All right, on to some R code and output. So this is an example from some data that came from a paper I wrote a while back on attitudes toward affirmative action policies. A number of predictors there. One of the predictors we're using is age, asking whether people support policies more as they get older. The predictor variable here is age, and we're predicting support for affirmative action policies. Again, if you want to look this up, it's from an article from way back in 2003. The code, I've just got at the bottom here. You can do this in a couple of different ways, but I've wrapped two commands here. Summary is just going to summarize the analysis and give us this output. The command for regression is LM, and the format is, again, data set $ variable. So the variable here is called support. And then we have the little tilde. Tilde is R for is predicted by. So what's to the left of the tilde is what you're predicting. What's to the right is what you're predicting it with. You can see the output that we get here. We get the intercept. It says 8.84. Not really, intercepts generally not got much useful information. And then the slope, 0.02 or negative 0.02. What this means is for every 1 year change in age, attitudes toward affirmative action go down 0.02 points on a 10-point scale. That's not much, is it? You would to go from one end of the scale to the other end of the scale to make a 10-point change, you'd have to be something like 500 years. It would have to be like 500 years old or something. So again, doesn't look like there's much relationship here. The R-square value is listed down below under multiple R-square, and one thing we see here is it's a very small value, 0.001, suggesting that we're not explaining support based on age very well. So a good plain English explanation here is that age doesn't tell us anything about support. And similarly, if we plugged in support for, say, a 34-year-old and support for an 18-year-old using the regression equation, we would find very little difference between those two groups. Both numbers are practically the same because we're not explaining anything. Age doesn't tell us anything about support. And you can see that graphically here, mostly flat regression line. All right, another analysis from these data looks at personal benefit or perceived personal benefit from affirmative action. And this had to do with a lot of questions. This isn't just, getting jobs, it's, enjoying your diverse workplace and things of that nature. And here we're asking, do people who perceive more benefit support it more? The predictor variable is perceived benefit. The predicted variable, the dependent variable, also known as the dependent variable, is again support for affirmative action. You see here the code just modified to reflect the new variables. Benefit has a slope of 0.44, so for every 1 point change in benefit, we see a 0.44 jump in support for affirmative action. Our R-square value is about 0.12, suggesting that we're explaining 12% of the variability in support based on knowing someone's perception of benefit. So a positive slope, people who see more benefit tend to support policies to a greater extent. And here we can show that when we have predictions for different levels, they do differ. If somebody scored a 1, their score on the affirmative action variable would be 6.85. If they scored a 14, though, their score would be predicted to be 12.5. So a real distinction between those two. And what we'll see here is that we have a steeper regression line. We have kind of big differences between the two ends in terms of benefit and support. All right, one last example. This is an example from a paper that did something you see a lot in psychology. It takes a It takes a phrase that people commonly use, like do opposites attract, like your hippie friend whose boyfriend voted for the current president. Nobody can explain why those two are together, but you know, people will often say, oh, well, opposites attract. So the authors of this study examined similarity and attraction. They had participants read descriptions of potential romantic partners and had them rate how similar they felt to that partner and how attracted they felt to that partner. And here's what their data look like. Probably a little bit easier when we take a look at our regression line. We can see based on the regression line that similarity is related to attraction. So you're more likely to be attracted to someone who you're more similar to. So opposites appear not to attract. And we'll see this in terms of our regression analysis. We're going to predict attraction from similarity. X variable is going to be similarity. Y variable is going to be attraction. You can see the code here. Attract predicted by similarity. Slope is 0.422 with a y-intercept of 28.8 and an r-square of 0.23. So explaining nearly a quarter of the possible variability in attraction just based on similarity. And you can see the regression equation, we can pull that out there. So one way we could use this, if we wanted to predict attraction, let's say we worked for, you know, whatever the online dating sites are, Match.com, well, with the old guy with the glasses who looks like a scientist. What if you worked for one of these sites? Your goal is to match people to people they find attractive. You know that the average score on the attraction scale is around 50 with a standard deviation of 10. You want to make sure that everybody has a partner that you expect them to rate as above average on attraction by at least 1.5 standard deviations. You have, and this is where you get into like these personality profiles that people have to fill out and things of that nature. I have everyone read descriptions of potential partners, rate them on similarity items. So how can we use this information to guarantee each person is paired with somebody they're attracted to? And of course, the answer is that we can use regression. Based on this regression equation, we need to figure out what sort of similarity rating is the minimum to produce a predicted attraction that's 1.5 standard deviations or higher above the mean. So the minimum to produce a 65 or higher. So just by doing a little bit of mathy stuff, we can find that X is somewhere around 86 or higher, produces a value of 65. So their similarity rating would have to be 86 or higher to guarantee a match. Now that certainly doesn't mean that everybody who rates a partner as similar as 86 or even higher is going to give them an above average attractiveness score, but it will on average do a lot better than just randomly assigning people. And again, that's going to be a function of the strength of the relationship. Bigger R square is going to be better prediction. All right, this is the end of this simple regression section. We'll have another few slides on multiple regression, which is the real workhorse within psychology, in next.